Ever since making appearance on the face of the Earth, man has painstakingly been learning about everything around. But even now, several hundreds of thousands of years later, we still cannot claim with certainty that our nearest space objects have been studied well enough. And probably the process of studying them will continue for many a century. As we look further from our system, we can observe objects that really defy our understanding. And I invite you to join me on a journey to several of these. We will fly by Mira, talk about brown and black dwarfs, take a look at Canis Venatici, the Methuselah star, the exoplanet Gliese 832c, and last but not least, witness the most tremendous explosions that have ever taken place in the observable universe. A fascinating journey is up ahead. Let's get started. Cosmo, the first in outer space. Most stars in the Milky Way slowly revolve around the center of the galaxy. Their appearance is rather recognizable and their speed is approximately the same as that of interstellar gas. Our Sun, for example, passes through the local interstellar cloud at a speed of about 25 kilometers per second. But Mira really stands out in this respect, as it whizzes through gas in interstellar space at a speed of 130 kilometers per second. As a result of such staggering propulsion, the shed material is blown back, thus forming the unique tail we can marvel at. This tail is the feature that makes Mira one of the most peculiar stars in the Cetus constellation. The tail of this star was discovered in 2007 with the help of the GALEX Orbiting Ultraviolet Space Telescope. A group of astronomers received high-quality ultraviolet light images of Mira where the tail, made up of gas and dust, can be clearly seen. At first, this tail formation rather perplexed the scientists, as the star had been under observation for over 400 years, and no tail had been spotted before. But the riddle was soon solved. Only ultraviolet images were able to reveal the tail, and only regular photos had been taken before. The length of the tail reaches 13 light-years, which is 3 times the distance from the Sun to the closest star, Proxima Centauri. As I've already mentioned, it was formed by material being shed in the course of the star's movement through space. Every 10 years, Mira sheds approximately as much material as the mass of our Earth. By estimating the length of the tail and the star's velocity, the material found at the very tip of the tail was gauged to have been dumped as long ago as about 30,000 years. As for the total mass of the material shed so far, it may be as much as 3,000 Earth masses. Marvelous as it is, the tail isn't the only feature that singles out Mira among other stars. Another feature it has is a bizarre formation that can also be seen in images beamed back from the GALEX telescope. It most likely originated as a result of Mira's speed with which it travels through the molecular cloud. A kind of bow we can see in front would have been accumulated in the many years as a result of the star's material at the front colliding with particles of interstellar gas. That makes Mira resemble a boat cutting through water, only Mira cuts through space instead. Most of the shed material is made up of atoms of hydrogen. Once shed, they gradually lose their impetus and release the energy in the form of ultraviolet rays, and it is these rays that were captured by the GALEX telescope. We know Mira as a binary pulsating variable star. In its maximal luminosity periods, it flares up to be the brightest star in its constellation, but even with its luminosity at its lowest, it can still be seen through regular binoculars. The best time for observing it from our Earth is October and November. Billions of years ago, this object used to be a yellow dwarf, and today, Mira's stellar travels are coming to an end, as it is now in one of the final stages of a star's life. Speaking about its system, it comprises 2 stellar companions, Mira A, a red giant, and Mira B, a white dwarf. Both objects are about 417 light-years away from our Earth, and the distance between the companions themselves is 70 astronomical units. The first component in the system is a pulsating variable star with the average apparent magnitude 3.5. Depending on the phase, however, the value may fluctuate between 10 and 2. Just to compare, the apparent magnitude of Sirius is -1.46. The mass of the system's first component is approximately 1.2 that of the Sun. Interestingly, its radius is 360 times that of the Sun. The reason for such impressive dimensions and a comparatively small mass lies in the fact that since Mira A is a red giant, its average density may be thousands of times less than that of water. Just to compare, the average density of the Sun is slightly bigger than that of water. Besides, a star hitting the red giant phase gets a massive growth spurt, and with a mass comparable to that of the Sun may in theory grow to the size of the Earth's orbit. The surface temperature on Mira A reaches 3000 degrees Kelvin. The luminosity of the star, meanwhile, is 9000 times that of the Sun. As for its supposed age, it is estimated to be 6 billion years. The red giant is not massive enough to go supernova at the end of its life cycle. Instead, it is going to expel its outer envelope and gradually turn into a white dwarf. The expanding outer envelope forms a planetary nebula, which will later on be dispersed in space around it. As for the second component, Mira B, it is a white dwarf already. As this object is located close to Mira A by space standards, it attracts material dumped from the outer layers of the red giant. In this manner, a hot accretion disk was formed around Mira B, and since matter is shed onto it at irregular intervals, Mira B is a variable star too. Its apparent magnitude fluctuates between 9.5 and 12. Thus, both components in the system are variable stars, or variables. Other stars in the universe, whose luminosity depends on physical processes taking place in their vicinity, also fall into the same category. It is important to study these objects in order to understand the nature of stellar evolution, as variable stars are more often than not at a turning point in their existence. In fact, the phenomenon of Mira is a perfect demonstration of how objects reaching some milestone or other in their life may conceal a number of great riddles. Mira's unusual features allowed scientists to use it as the prototype for a special classification for such-like objects that got the name Mira-type stars or Mira variables. Celestial objects of this variety are pulsating variable stars of late-type spectral classes, with the values for their apparent magnitudes ranging from 2.5 to 11. Mira variables are giants that shed their outer envelope in the course of several million years and eventually turn into white dwarfs. Mostly, Mira-type variables shouldn't be heavier than 2 masses of the Sun, although they may be thousands of times brighter than the Sun on account of their expanded outer layer. The pulsation of these objects occurs due to regular contraction and expansion of these stars. This also causes changes in the radius and temperature, resulting in variable luminosity. As for the chance of planets possibly hiding somewhere in these stars' orbits, only one Mira-type variable boasts an unconfirmed planetary system, R Leonis, in the Leo constellation. It goes without saying that the information about Mira possessed by science today is rather sparse. We really have no clue if there are planets or some equally amazing space objects located close to it. But it is safe enough to say that this star is yet to hit the headlines, and for all we know, it may happen literally at any moment. It may be hard to imagine, but our Sun, which is relatively small for a star, is heavier than any of 95% of stars in the universe. There are also such things as red dwarfs, 11 times lighter than our host star. However, they're actually not the lightest objects out there. In the wide range between gas giants and the smallest stars in the universe, there are some fascinating objects known as brown dwarfs or dwarf stars. To understand their nature, let's have a look at how a star is born. According to modern scientific theories, stars and brown dwarfs originate in the same star nursery. When nebulae made up of interstellar gas gradually contract under the influence of gravitational forces, pressure and temperature inside the gas increase. The enormous nebulae disintegrate into a great number of protostellar disks, and each of them has a chance of becoming a fully fledged star at some point. Its destiny depends on how much matter the young star will manage to capture. If the mass of a protostar is over 8% of that of the Sun, thermonuclear reactions are bound to start in its interior. Nuclei of light elements like hydrogen, deuterium, helium or lithium blend together, emitting a great amount of heat. This heats up the interior of the future star even more, and more matter is involved in these processes. This unleashes a chain reaction which may persevere for billions of years until the substances fueling it are totally depleted. And so a new star is born somewhere light years away from us and can probably be observed in the sky. Its future depends on its mass and chemical composition. Most of its life cycle will be spent in the main sequence phase. Later, the star is likely to turn into a white dwarf, or alternatively a neutron star or a black hole. But what if the mass of the forming protostar is smaller? Then the gravitational pressure will not be enough for the heat produced by the thermonuclear reaction to increase the star's temperature to the point when it is able to sustain the burning process without additional help from other sources. Nuclear fusion will still take place, but the heat emitted during the process will not be enough for the star to flare up. Instead, the object will slowly decay until the substances necessary for thermonuclear reactions are depleted. It's worth mentioning that every kind of reaction requires a certain temperature to initiate nuclear fusion. If the star's temperature is lower, nuclei will not be able to get closer and will be mutually repelled by Coulomb force. The celestial object we're looking at today is what is known as a brown dwarf in space. Interestingly, in spite of their name, not many of them are actually of a brownish hue. If we could look at them with the naked eye, we would most likely see them crimson, orange or even black, the color depending on the surface temperature. The hottest brown dwarfs have a temperature not higher than 3000 degrees Kelvin, which corresponds to a faint red glow. Most of them are much colder, from 300 to a couple of thousand degrees Kelvin. The peak in their radiation is in the infrared range, which is invisible to the naked eye. Just to compare, the coolest star's surface temperature is about 4000 degrees Kelvin. By radiating heat into its environment, a brown dwarf gradually depletes its energy and cools off. Thermonuclear reactions in its interior die down, and the object turns into a ball of compressed gas. It will cool off gradually and will resemble a gas giant of impressive dimensions. After its heat is slowly dissipated, a brown dwarf may in theory cool off to as little as 4 or 5 degrees Kelvin, the background temperature of the universe's relic radiation. However, the temperature of the coolest space objects of this variety that have been discovered are about 300 degrees Kelvin. There are several celestial objects that may yet earn the title of a brown dwarf. One of them is WISE 1828 +2650. It is in the Lyra constellation and is 47 light-years away from the Sun. It is considered the coldest brown dwarf to have been discovered, although astronomers make scientific contributions every day, and perhaps we will soon hear of still cooler objects. A brown dwarf's dimensions are usually comparable to those of Jupiter, while its mass is several dozen times that of Jupiter. For example, the object Corot 3b in the constellation Aquila, about 2200 light-years from the Earth, is similar to Jupiter in its diameter but is 22 times heavier. A space object qualifies to be called a brown dwarf if its mass is approximately 12.5 to 80 times that of Jupiter. Objects heavier than that are red dwarfs. Those lighter than that are sub-brown dwarfs, super Jupiters and planemos. It goes without saying that such small and dim celestial bodies are practically impossible to see with a regular telescope. The existence of these fascinating objects was predicted back in the 1960s, although even special infrared detectors were unable to spot brown dwarfs for a long time. Many years passed before the first brown dwarf had been detected. The great event took place in 1995. The find was an object dubbed Teda 1, a rather hot celestial body for its class. It is located in the constellation Taurus, approximately 400 light-years away from the Sun. Its surface temperature reaches 2700 degrees Kelvin and its mass is 55 times that of Jupiter or 5.2% that of the Sun. In the years that followed, a great number of other celestial bodies of this class were discovered. About 100 of them were detected within as little a radius as 60 light-years from the Sun. The total number of brown dwarfs in our galaxy is estimated at 50 to 100 billion, which accounts for about a quarter of the overall number of stars in the Milky Way. The brown dwarf closest to the Earth is just 9 light-years away from the Sun. Brown dwarfs are rather cool objects by stellar standards. That is why they may contain complex compounds like methane. As for the temperature of the coolest main sequence stars, it is so high that electrons leave their nuclei and thus the substance turns into scorching plasma. Even the simplest two-atom molecules like hydrogen cannot endure this harsh environment. There may be planets orbiting brown dwarfs. The first satellite of this kind was detected in 2004. It orbits 2M1207, a comparatively warm brown dwarf in the constellation Centauri, which is 64 parsecs or 209 light-years away from the Earth. This planet is rather large. Its mass is 4 times that of Jupiter. Can the planets orbiting brown dwarfs be habitable? It is posited that the chances are slim, but theoretically it is feasible. Since brown dwarfs are much cooler than stars, their habitable zone is narrower, concentrating closer to the parent dwarf. Also, it should be noted that the eccentricity of the satellite planet's orbit should be low, that is, practically ideally spherical in shape. Since a brown dwarf is constantly in the process of cooling, its habitable zone gradually shifts closer to it. According to some estimates, a rather heavy and hot dwarf may sustain conditions suitable for life on its satellite planet for as long as 10 billion years. But of course, there are admittedly many other objects in the universe which are definitely more favorable for cultivating life. The term stellar evolution in astronomy refers to the sequence of changes that a star undergoes throughout its entire life. This process largely depends on the object's initial mass, and may take anything from several million to tens of billions of years. As a rule, a star originates from a cloud of cold, low-pressure interstellar gas. Due to gravitational instability, the cloud compresses and eventually slowly assumes a spherical shape. During the compression process, the gravitational field energy is transformed into heat and radiation, with the temperature of the young star gradually going up. The duration of this stage depends directly on the star's initial mass. With the heaviest stars, it may take about 100,000 years, and with the lightest ones, the phase may last up to several billion years. Our Sun's mass, for instance, is comparatively small, and so it remained in this first phase for approximately 110 million years. In the next phase, after a sufficiently high temperature has been reached at the core, thermonuclear fusion takes place inside the star and the compression ceases. After this, the processes taking place at the core become the star's only energy source, and thus a young star, which is also called a protostar, becomes a main sequence star. This is the starting point for calculating a star's age, as this phase accounts for approximately 90% of its life cycle. Our Sun, for example, will remain in the main sequence stage for approximately 11.5 billion years. When a star enters its main sequence stage, its chemical composition is still very close to interstellar environment and is 91% hydrogen. At the same time, the process of hydrogen transforming into helium is constantly in progress inside the star. As a result, the core compresses and gains in density, which gradually increases the rate of chemical reactions. It leads to noticeable changes in the star's properties. For example, the luminosity of our Sun in the main sequence stage accounted for only 70% of its luminosity today. By the time this stage is over, the luminosity is going to be 2.2 times that of today. It should be mentioned that not all stars make it to the main sequence stage. The exceptions known to science today are referred to as cold and hot subdwarfs. These objects are very similar to main sequence stars, but they do differ from them. Thus, by contrast, subdwarfs are not rich in heavy elements and are not so luminous. The final phase for main sequence stars also depends on their mass. Generally, a star either discards its outer coat, thus becoming a white dwarf, or goes supernova to later become a neutron star or a black hole. A supernova is a phenomenon when a star's luminosity dramatically intensifies, with great amounts of energy released during the process. After that, the flare slowly fades. This explosion is accompanied by emissions of great amounts of matter from the outer coat. The remaining matter in the core of the star gone supernova generally forms a compact object, either a neutron star or a black hole. Apart from everything else, the matter released in the course of a supernova event contains products of thermonuclear synthesis. It is thanks to these elements that the universe is able to evolutionize chemistry-wise. If a star's mass doesn't quite reach 8 sun masses, however, this main sequence star will end up being a white dwarf. That is, an object which is a hot celestial body of small dimensions and a high density. For instance, in the case with our Sun, when the time comes for it to go through this phase, it is going to become 100 times smaller than it is now. White dwarfs do not generate energy and are luminous only on account of their high temperature. Even though the hottest white dwarf's surfaces may be as scorching as 70,000 kelvins, due to their small size, their luminosity is not that great. As for their average density, it is almost 1,000,000 times that of the regular density of main sequence stars. These objects consist for the most part of a plasma of nuclei and electrons, and are completely devoid of thermonuclear energy sources, which is why they gradually cool off and assume a red hue. Sirius B is the closest white dwarf to us that we currently know of, and it is 8.6 light-years away. This object's mass is give or take that of the Sun and is considered to be one of the most massive white dwarfs known today. Its volume is 1/1,000,000th of that of the Sun, and its dimensions are identical to those of our Earth. Sirius B is believed to have become a white dwarf approximately 120 million years ago, with the initial mass of the star in its main sequence phase having been 5 sun masses. Today, it is posited that these objects account for 3 to 10% of the overall stellar population of our galaxy, according to different estimates. Over 97% of the stars known today are eventually destined to become white dwarfs. As time goes by, these objects are bound to cool off and fade. Eventually, all celestial bodies of this variety will become black dwarfs, which implies that they will completely cease to emit any visible light. This process takes scores of billions of years. That is why to date science hasn't had a chance to observe any of these objects. The universe is considered to be too young to have produced any black dwarfs at this point, but scientists have already managed to spot objects quite similar to them, whose temperature has gone down lower than 4,000 kelvins. These objects are white dwarfs WD 0346+246 and DES DSS J110-217. A black dwarf is what most stars look like at the final stage of their evolution. Its mass is quite identical to that of a white dwarf. According to today's models demonstrating cooling of these bodies, white dwarfs formed in the course of the evolution of the first generation of stars are supposed to have a temperature of approximately 3,200 kelvins and to appear as rather dim objects. For all we know, these celestial bodies could be part of the universe's hidden mass components. For a white dwarf to cool off to the temperature as low as 5 kelvins, it may take approximately 1 quadrillion years. In theory, when black dwarfs cool off completely, the process of dark matter annihilation becomes very important for their existence. This phenomenon hasn't been directly observed in the universe yet, although it is thought that in the course of annihilation, particles of dark matter will form ordinary photons and emit light visible through a telescope. Without allowing for this phenomenon, black dwarfs are believed to cool off and fade to the point where their temperature equals the background temperature of the universe. However, in theory, thanks to the energy derived from dark matter annihilation, black dwarfs may well continue to radiate energy for a considerably longer period, and thus enjoy their luminosity longer. The process of dark matter annihilation in these objects is thought to continue for as long as the galactic halo remains whole, and that means for over a septillion years. After that, dark matter annihilation gradually ceases, and only then will black dwarfs cool off completely. It is likely that mankind will never be able to discover objects of this kind, as the main period of their life takes place in the phase and the life of our universe which will come after the one we're in at the moment. The period we live in is a star epoch. That is the period where stars are still born quite actively. This epoch will last up until the point when the galaxies will deplete all of their interstellar gas. After that, it will be the turn of low-mass stars like our Sun to fade. Following that, a long period of disintegration will begin, when white, brown and black dwarfs are the main objects populating the universe. At the next stage, the epoch of black holes, all matter in the universe will be transformed into elementary or subatomic particles, with the remaining black dwarfs getting sucked in by black holes or completely disintegrating. The final stage in the life of the universe is supposed to be the epoch of eternal darkness, where there won't be any energy sources whatsoever in space. The overall temperature in the universe will reach absolute zero. Space will gradually expand, and in the light of the last and rare black holes, in about 1 Gogol years, our world will come to its gloomy end. By that time, all traces of what was once the human civilization would have become nothing. However, if we can influence the process of the universe's evolution in any way, the course of its life may be significantly altered. Just imagine what a stupendous portion of our cultural heritage would never have been around. A great number of myths and legends have to do with the stars. It goes without saying that any travels to other stellar systems would be out of the question. Even a few light years is an overwhelming distance for man even at this point of our scientific progress. As for covering several 100 million light years, the mere thought is no more than just a fanciful dream. It would take man inventing extremely powerful and advanced telescopes to be able to see that the Sun was not the only star in our universe. But would they ever be invented? There is no way of finding it out, especially if we take into account the fact that it is stars themselves that have always been a powerful stimulus for man to try to get to the bottom of the nature of the universe. Chances are that a bleak, dark sky would never have fascinated people, and as a result, no modern devices and equipment for observing space would ever have been developed. In one of our previous videos, I've already told you about gargantuan cosmic voids, or else I take it you would have heard about these. Voids are large-scale expanses of space that are almost or completely devoid of galaxies or galaxy clusters. These enormous objects take up about 50% of the observable universe. The average void measures approximately 40 megaparsec, or 130 million light-years. However, the diameter of champion voids may reach several 100 million or even a billion light-years. These extra-large voids are rather predictably referred to as supervoids. The density of matter in these regions is much less than in other areas of the universe and accounts for less than 10% of the average density in meta-galaxy. Voids are the largest formations among the large-scale structures of the universe, on a par with galactic filaments or thread-like formations. Cosmology today explains their existence by diversity of matter when the universe was formed. One of the largest voids ever discovered is the Canis Venaticis supervoid. Spotted in 1988, this supervoid is the second largest void known to science today. With a diameter measuring a staggering 300 to 400 megaparsec, or a billion light-years, the Canis Venaticis supervoid is located 1.5 billion light-years away from our Earth. Interestingly, just 17 galaxy clusters are located in this area of mind-boggling dimensions, and this is extremely little for such an incredibly enormous expanse of space. All the 17 clusters are gathered within a comparatively small area by space standards, namely within a measly 150 million light-years. If any gravitational interaction between them does take place, more advanced technologies are called for to detect it. The diameter of the Canis Venaticis supervoid accounts for approximately 1% of that of the observable universe. It could easily accommodate 10,000 galaxies identical to the Milky Way in terms of dimensions. Who knows, perhaps there are life forms on a planet hidden somewhere in these 17 clusters. However, there is no way light from our Sun will ever reach those parts, and any interaction with potential inhabitants of those parts of the universe is effectively out of the question. Now, what is a billion light-years? The history of multicellular life forms on our Earth, starting from primitive coelenterate animals, counts just over 800 million years. In other words, life on our planet evolved from colonies of protozoans to humans in the time a photon traveled from one edge of the supervoid to the other. It takes some stars less time to complete their entire life cycle, from getting born to going supernova or finishing life in an alternative way. Actually covering this distance in a spaceship, romantic as it is, sounds like a recklessly eccentric idea. In order to understand what space inside a void is like, you have to think of a deep physical vacuum. It may contain interstellar gas clouds, independent star clusters, or even galaxies, but most of the supervoid contains nothing. The name is self-explanatory. Of course, space expanses are for the most part vacuum. Just to give you an idea about the proportions, there is a cubic centimeter of dense stellar matter to thousands of cubic kilometers of space. But even this space is not completely empty. A mark of 100 kilometers above ground is the accepted limit of the Earth's atmosphere. At this height, the atmospheric pressure is so small that it becomes comparable to that of solar wind. However, there is no clearly defined transition to space, and even several hundred kilometers above the Earth's surface, there can be found an extremely small amount of gas molecules from our atmosphere. Seemingly negligible, these molecules still manage to slow down artificial satellites orbiting our planet. As a result, many of them have to regularly adjust their orbit in order not to lose their momentum and not to have to get back to Earth prematurely. Gas concentration is much lower the further we are from a planet. But even beyond our solar system and away from any star or planet, there will always be at least a few molecules of hydrogen in every cubic centimeter of space. In addition to that, there will be solar wind in space, a current of high-energy subatomic particles emitted by the Sun. And of course, other things have to be reckoned with, like radiation of distant stars, relic radiation, and neutrinos, subatomic particles particularly hard to detect. The vacuum inside the void is deep to such a point that there is less than half a molecule of matter for every cubic centimeter of space. Besides, all sources of radiation are so remote from it that the density of their radiation is quite negligible compared to relic radiation. As a result, all that remains is undetectable neutrinos and the cosmic microwave background. As I've mentioned before, there is something else to be found inside the incredibly vast expanses of the void apart from deep vacuum. There are also clouds of interstellar gas, the future nursery for stars and galaxies. Secondly, dark matter is supposed to be found inside supervoids, but today's methods of detection are hardly adequate for studying it. It should be noted that the overwhelming majority of voids detected so far are located hundreds of millions of light-years away from the solar system. In essence, what we are observing now is the distant past of these formations. Only one void lies relatively close to the local group of galaxies, among them the Milky Way, and is referred to as the local void. Its diameter measures approximately 180 million light-years, and the distance between the Sun and the void's center is about 90 million light-years. The Boötes void is another large formation about 700 million light-years away from the Sun. The diameter of this void measures approximately 330 million light-years, which is about 0.35% of the diameter of the observable universe. The Boötes void was discovered in 1981 by a group of scientists headed by Robert Kirshner, with theoretical arguments in favor of the existence of supervoids having been formulated 20 years previously. The supervoid is thought to have been formed as a result of several smaller voids blending together. Just 60 galaxies have been pinpointed inside the Boötes void by now, although such staggering expanses could easily have accommodated about 2,000. Speaking about the most mysterious void in the universe, it lies 3 billion light-years away from the Sun. It is known as the CMB cold spot or the Eridanus supervoid. This supervoid is a champion even by supervoid standards. With a diameter measuring 1.8 billion light-years, it may easily have accommodated 18,000 galaxies similar to the Milky Way. The Eridanus supervoid's temperature is from 70 to 150 degrees microkelvin colder than the average CMB temperature of the universe. Today's theory of the universe's origin cannot give a definite explanation to this fact. This so did not fit into the accepted theory in cosmology that at first the measurements were dismissed as faulty and the equipment was blamed. Only after several years of scrupulous measurement were the readings finally accepted. A great number of explanations, including rather extravagant ones, were offered concerning the strange temperature properties. One hypothesis has it that the anomalously low cosmic microwave background in the Eridanus supervoid is a result of the influence of supermassive chunks of dark energy. According to another hypothesis, this area is what is left of another universe that had existed before ours. Be it as it may, there is disappointingly no definite answer yet. As I've already mentioned, the universe is over 13.8 billion years old. So how can it possibly contain a star older than itself? For more than 100 years, astronomers have been observing a strange star 190 light-years away from the Earth in the constellation Libra. It travels at a speed of about 1.3 million kilometers per hour. But its most peculiar feature is its age. HD 140283 is considered one of the oldest stars in the universe known to science today. In the year 2000, scientists tried to estimate its age. They were guided by data that had been collected by the Hipparcos satellite launched by the European Space Agency, and thus they got the figure of 16 billion years. The generally accepted age of the universe was 13.8 billion years, which had been confirmed by observations. The discrepancy between the two values prompted a lot of debate. How can a star be older than the universe? Or else, how can the universe be younger than a star? As for its unusual name, the star was dubbed after a biblical character Methuselah, who according to scripture lived to be 969 years old. The star Methuselah is clearly genuinely old. It is none other than a subgiant consisting mainly of hydrogen and helium. It contains a negligible amount of iron, which may only mean that this object was formed before iron had become such a widespread element. But how can a star be about 2 billion years older than the environment it finds itself in? It appeared to be a perplexing paradox. Astronomer Howard Bond and his colleagues from Pennsylvania State University proceeded to double-check the value of the star's age. They too were struck by the fact that Methuselah had been born before the universe. In their task, they had to go through 11 observational datasets collected in the period from 2003 to 2011 by the Fine Guidance Sensors of the Hubble Space Telescope. The sensors measure stars' positions, distances, and radiation energy. It is possible to produce precise results in estimating the age of an object by studying its parallax and using spectroscopy and photometry. According to Bond, not knowing the precise distance to HD 140283 remained one of the reasons the age may have been gauged wrongly. The distances had to be scrupulously measured in order to calculate the object's luminosity with a view to estimating the object's age. The brighter the star, the younger it actually is. The scientists were also studying the parallax and keeping watch on the star's position in the sky for a year. Theoretical models also left a lot to be desired. The scientists were uncertain as to the precise rate of nuclear reactions and couldn't put their finger on the role of diffusion of certain elements in the star's outer layers. That is why the team considered the possibility of a faster thermonuclear synthesis. If the star really burned faster than ordinary ones do, then it was supposed to be really younger than previously estimated. Bond added that oxygen at HD 140283 also had to be reckoned with. The ratio of oxygen to iron was rather high, and in the first millions of years of the universe's evolution, there wasn't that much oxygen around. This was another piece of evidence confirming Methuselah's younger age. Eventually, the value Bond and his colleagues produced was 14.46 billion years plus minus 800 million years. This, of course, is significantly less than 16 billion, but still more than the age of the universe, not counting the margin of error of 800 million years. According to Robert Matthews, a British physicist from Aston University in Birmingham who wasn't on the research team, the estimates may have been corrupted by both accidental and systematic errors. The most precise, up-to-date value of the star's age was in conflict with the age of the universe calculated using relic radiation. The conflict could be resolved only by giving the result the larger margin of error. In later research, the star was gauged to be still younger. In 2014, a study titled Sequel was published, where the authors lowered the estimate of Methuselah's age to 14.27 billion years, but admittedly there was still the margin of error of 700–800 million years. Strangely, the star's age still beat that of the universe. According to Bond, the similarity between the values of the age of the universe and its oldest star proves the consistency of the Big Bang theory. Besides, the values were produced by different methods of analysis. Thanks to meticulous observations, the results are not as scattered as they were in the 1990s, when ancient stars were estimated at 19 or even 20 billion years. At least now, the inaccuracies do not clash with the accepted models. Robert Matthews, however, maintains that the issue is anything but solved. As recently as in July 2019, scientists participated in an international cosmology conference at the Kavli Institute for Theoretical Physics in Santa Barbara, California, where they analyzed studies of the universe's supposed age. Judging by the galaxies nearest to us, the universe is several hundred million years younger than suggested by the results of relic radiation calculations. Moreover, for all we know, our universe may turn out to be just 11.4 billion years old, and the new estimates shouldn't be casually dismissed. After all, one of the authors was a Nobel Prize laureate, astrophysicist Adam Rees from the Space Telescope Science Institute, STSCI. The conclusions are drawn on the concept of the universe's expansion suggested by Edwin Hubble back in 1929. The expansion of the universe is a fundamental concept in the Big Bang theory. If the universe has always been expanding, shouldn't there be a starting point for the process that could be calculated? According to the latest data, the rate of expansion is in fact 10% higher than suggested by Planck. According to Planck's team, the rate of the universe's expansion is 67.4 kilometers per second per megaparsec. The latest measurements produced the value of around 73-74 km per second per megaparsec. Riess maintains that there should be a difference between the real rate of expansion today and the rate implied by the physics of the early universe. Firstly, it is obvious that accepted theories have to be seriously questioned. And secondly, there is the dark matter and dark energy riddle. Since the Hubble constant produces a bigger value for the rate of expansion, it suggests that the universe is younger than we think. The 67.74 constant corresponds to the age of 13.8 billion years. The 73 or even 77 constant corresponds to the age of not more than 12.7 billion years. Quite recently, a study was published in the Science magazine which claims the Hubble constant to be 82.4. It should be mentioned it's a well-reputed magazine. The 82.4 constant corresponds to the age of 11.4 billion years. Either way, the star HD 140283 still appears older than the universe. Matthews believes this is a task to be handled by cosmologists rather than astrophysicists. To define the age precisely, it isn't stars that have to be studied, but more complex structures of the universe. So why would the universe appear younger than this one star? Matthews suggests at least two possible explanations. As is so often the case with the history of science, the end result is likely to turn out to be a combination of the two versions. In short, there may be observation errors caused by something we do not fully understand, and also there may be some blanks in our knowledge of the universe's dynamics. For example, the dark matter force, which as it were has been in charge of the expansion of the universe for billions of years, is still rather baffling to us. Thus, the age paradox could well be accounted for by dark energy variations and changes in the expansion rate. According to theorists, all this may have to do with the fundamentals of the nature of gravity, in particular the causal set theory, which leads us to believe that by measuring gravitational waves, we may get to the bottom of the paradox. Gravitational waves are hard to measure. Just to give you an idea, they were first detected as recently as in 2015. Astrophysicist Stephen Feeney from the Flatiron Institute believes that a major scientific breakthrough on this front may take place in the next 1,000 years. And the bizarre phenomenon of the age of HD 140283 is bound to reveal larger and more scientifically complex things that are yet to be discovered and explored. Today we're able to access a lot of information about space objects, discoveries in astronomy and studies of prominent scientists. It is quite within our power to share this information and bring as many inquiring minds up to date as possible. This is a kind of landscape one would see in the least harsh part of a planet dubbed by scientists as Super-Earth and the closest potential candidate suitable for searching for alien life forms. But let's be consecutive. The recent past heralded a boom in discovering exoplanets. There are 4,370 exoplanets discovered in over 3,000 planetary systems so far. In addition to these, more than 3,000 objects are awaiting confirmation of their exoplanet status. Most of them are large bodies, gas giants, super-Jupiters and super-Earths. This is accounted for by technical features of the technologies used for the purpose. It is easier to look for massive bodies with a short orbital period than to try to spot smaller planets similar to the Earth or Mars in terms of dimensions. There are among exoplanets those that may realistically harbor life. There are dozens of these objects scattered in space, and they understandably draw scientists' close attention. Today we're going to look at one of these objects, which is an exoplanet dubbed Gliese 832c. In fact, this exoplanet is one of the most likely places where alien life forms will eventually be detected. This exoplanet orbits a star called Gliese 832, which lies 16 light-years away from the Sun and is part of the Grus constellation. Gliese 832 is a dim red dwarf whose luminosity is just 0.7% of that of the Sun. Both its mass and diameter are approximately 2 times smaller than those of the Sun, and its temperature reaches about 3,300 degrees Kelvin. That is the reason why the habitable zone of this planet is within quite a short range from its star. Due to tidal forces, the planets lying in the habitable zone of Gliese 832 will be tidally locked to their star, that is, will face the star with one side only, just as it is the case with the Moon and the Earth, and Mercury and the Sun. There are 2 confirmed planets orbiting Gliese 832. The Jupiter-like planet Gliese 832b was discovered first. Astronomers announced the event in 2008. With the mass 2/3 that of Jupiter, the planet orbits its parent star at a distance of an average 3.4 astronomical units, completing a full orbit every 9.4 Earth years. The discovery of the other confirmed planet, Gliese 832c, was announced in 2015 by an international team of scientists headed by Robert Wittenmeyer. It got an exceptionally high rating for its similarity to the Earth, 0.81 to be more exact, which instantly attracted both scientists and reporters. It was also nicknamed the Second Earth, even though the 2 planets' parameters are rather different. Either way, this is one of the planets closest to the Earth with such a high Earth Similarity Index. The mass of Gliese 832c is 5.5 that of the Earth. It takes the planet 35 Earth days to complete a full orbit around its parent star, moving at a distance of an average 0.16 astronomical units. This is 6 times less than the distance between our Earth and the Sun. Its orbit's eccentricity is rather high, with the planet regularly leaving the habitable zone and then re-entering it. This must cause sharp temperature leaps and drops on its surface. Gliese 832c is estimated to receive approximately as much energy flux from its parent star as does the Earth from the Sun. The average surface temperature on the planet is 253 degrees Kelvin or 20 degrees Celsius below zero. It is also suggested that due to the atmosphere, which is likely to be quite dense, the temperature on the planet may be considerably higher. However, it is not easy to claim this with certainty, as Gliese 832c lies quite close to its star, and so chances are it is firmly tidally locked to it. In this case, there should be a substantial temperature difference between its sunny side and shadow side, which should regularly cause hurricane winds if the atmosphere really is dense. It's worth mentioning that in 2017, following observations, astrophysicists from the University of Texas at Arlington, the USA, put forward the hypothesis that there may be a 3rd planet in the Gliese 832 system. Its mass could be 1 to 15 Earth masses, and it could follow a stable orbit around the center of the system 0.25 to 2 astronomical units away from it. At the moment, the planet is being searched for. Let's imagine what Gliese 832c would look like assuming life were possible on this planet. First of all, we wouldn't help noticing its gravity, which would be strikingly higher than that on our Earth. Since the planet's diameter is not yet known, the gravity force cannot be calculated exactly. Still, it would be a rocky planet similar to our Earth and Earth-like planets in terms of its density, so its gravity force would be likely to reach 2 to 400% that of the Earth. This would lead to the relief leveling out, meaning that the mountains would not be so high and the oceans not so deep. This in its turn would enhance the area of warm water, which is favorable for life. Due to a dense atmosphere and a comparatively dim sun, the landscape on Gliese 832c would be of a reddish hue, and in general the planet would be submerged in semi-darkness. Since the planet is likely to face its star with the same side at all times, the temperature on the sunny side should be high and the temperature on the shadow side quite low. In the ring-like area at the border between them, the temperature should be moderately comfortable, although due to irregular heating of the planet, the atmosphere would be constantly in turmoil, which should result in strong winds. In addition, high objects of relief potentially able to dissipate some of the force of hurricane air currents fail to form on account of high gravity conditions. As the orbit of Gliese 832c is small and elongated, seasons on this planet should change every week. It will be winter on Gliese 832c at the furthest point from its parent star, and summer at the closest approach. The tilt of the rotational axis with respect to the ecliptic plane will not be of such importance as it is in the case of the Earth. The change of season will depend exclusively on the planets getting closer to or away from its parent star. The most favorable conditions for life to develop on Gliese 832c are likely to be in the ring-like area at the border between the light and the dark sides of the planet. It is here that most liquid water will accumulate and rain down from clouds formed on the warm side. Ice caps on the dark side will also melt in the border zone, thus supplying still more water. It goes without saying that it is water that is key to developing life. The change of seasons will be likely to play the same role as lunar tides on our Earth, with areas alternately submerging and re-emerging. This process of water getting mixed with substances dissolved in it is a good prerequisite for life to originate and develop. There is a good chance of life originating in water and probably staying in it without later spreading to land. The ocean reduces the effect of gravity and protects its potential inhabitants from sharp temperature changes and hurricane winds. As for frequent and sharp changes of seasons, hypothetical organisms on Gliese 832c may learn to lapse into a state of anabiosis in order to weather unpleasant, although short, periods of high and low temperatures. Alternatively, they may choose to emigrate to a comfortable temperature zone, from the sunny side to the shadow side and back again, for example. If a space probe ever reaches the surface of Gliese 832c to investigate the area, what would it see there? Assuming life did originate on this planet, as the gravity forces are rather strong there, the potential inhabitant should be a thick-set, chunky figure boasting a robust skeleton and powerful muscles. Plants on Gliese 832c would be dark in order to attract as much light as possible. They should also be quite low and likely to be creeping or moss-like, with strong roots able to stand winds. It is highly likely that rather than chlorophyll, some other molecules should be important for photosynthesis. The planet's dense atmosphere may become a habitat for bizarre life forms floating in air currents. Single-celled microorganisms, for instance, may float in this dense atmosphere following air currents, while capturing light and nutrients dispersed in the air. Because of a dense atmosphere, high clouds and a dim sun, the surface of Gliese 832c would be a rather dark place. Life forms would have to adapt to these conditions. Vision would probably not play the decisive role in their existence, if it evolved at all. Alternatively, its spectrum may be limited to the infrared range. Be it as it may, all these speculations remain conjectures and ideas, even though they're based on good physical laws and assumptions. I wonder which of these suggestions you would call realistic and which of them bordering on fantasy. Or perhaps Gliese 832c is not habitable at all? Let us know in the comments, and let's keep in touch. To begin with, let's define what the Big Bang actually is and estimate how much power may have been released in this process. The concept of the phenomenon referred to describes the accepted cosmological model of the genesis and early life of the universe, namely, the beginning of the universe's expansion after an undefined period of being in the state of singularity. The state of singularity is the state of the universe when the density of energy was large and the space-time curve was sharp. These figures reached the Planck values. The Big Bang, on the other hand, is said to have been the starting point for the process of this energy getting released. This event can't have been anything like a dynamite stick going off in empty space. Besides, it took place literally everywhere at the same time, and it's hardly possible to pinpoint the epicenter. It is indeed hardly possible to say with certainty how it really happened and what it looked like. But one thing is clear. This was an ultimate event of enormous proportions. We're talking about an explosion that is considered to have given birth to the entire universe. In the centuries of the history of space observation, science hasn't registered any other event similar in its proportions. However, as our technologies became more advanced, scientists came to realize that there are some events taking place in deep space which are powerful to such a point that it appears that all existing models need to be questioned. One of these breakthrough discoveries was gamma-ray bursts, or GRBs. The term traditionally refers to large-scale energy emissions in space, which in fact are an everyday occurrence in the cosmos. Gamma-ray bursts are the most powerful of explosions known to science taking place in space. Shockingly, the energy released in a few seconds is tantamount to that released by the Sun in the course of 10 billion years. It was next to impossible to register gamma-ray bursts for 30 years. Even though some attempts revealed a rather exact location of a source, sources were always scattered and didn't repeat in one place. A burst didn't leave any traces whatsoever, and the best scientists could do was to identify some really remote galaxy where a burst was registered. Only in 1968 was it possible for scientists to put their finger on the phenomenon of gamma-ray bursts, all thanks to the Vela satellites of the US Air Force, whose mission was detecting possible nuclear tests in the atmosphere. According to today's views, gamma-ray bursts occur when massive stars go supernova and collapse to black holes. A powerful stream of charged particles bursts out from the hole's vicinity. On interacting with magnetic fields and cosmic radiation, these particles produce gamma rays as a result. This stream of gamma rays is powerful to such a point that such events are easily detected by satellites, even though they may have taken place several billion light-years away. On the other hand, they can't be registered by Earth-based telescopes on account of the atmosphere, which actively absorbs these rays. The amount of energy released in the course of a gamma-ray burst may reach a septendecillion ergs. If an event of such tremendous proportions were to take place close to a planet, it would be tantamount to an atomic bomb exploding in every hectare of the sky. Of course, all living things would almost certainly die instantly. A gamma-ray burst is capable of exterminating any life within the radius of tens and even hundreds of light-years, and seriously affecting biospheres of planets within the radius of thousands of light-years. Thankfully, they occur a bigger distance away from us. For example, one of the most powerful gamma-ray bursts ever detected, dubbed GRB 180720, is more than 4 billion light-years away from us. This means that its light has traveled to our Earth for about 1/3 of the universe's age. As for the amount of energy in this gamma-ray burst, it fluctuates between 200 to 1,000 billion electron volts. Just to compare, the energy of visible light is in the range from 1 to 3 electron volts. At a distance of tens of thousands of light-years, a gamma-ray burst like that is practically harmless, but 1 out of 100 or 1,000 flares in a galaxy may occur close enough to a planet to pose a threat. Speaking about a threat to our own planet, scientists are still at odds if an explosion like that may dramatically affect it. For example, according to some calculations, gamma-ray bursts are really capable of seriously and noticeably affecting the Earth's fauna every several hundred million years, and one of these flares may have been the cause of a major mass extinction event. However, science is more keen on investigating the nature and origin of such bursts. Today, it is posited that, as a rule, gamma-ray bursts occur following the collapse of a really massive star, or else when two neutron stars merge and collapse together to a black hole. A gamma-ray burst event doesn't much differ from a supernova event in this respect, as both of them involve a gravitational collapse of a star's core. The difference lies in the consequences. In the case with a star going supernova, a hard layer of matter is shed, which travels with a speed of 10 to 30 kilometers per second. As for a gamma-ray burst, something emitting gamma quanta travels practically at the speed of light. An event like that isn't likely to occur anywhere close to us, Be it as it may, a great number of events of a similarly large scale occur in the cosmos, and they may well take place comparatively close to us. One of these could be a star-going supernova, a phenomenon when a star's apparent magnitude intensifies 10 to 20 times. This process is the ultimate destructive event taking place at the end of some star's evolution and is accompanied by the release of great amounts of energy. A supernova event is accompanied by emissions of substantial amounts of matter from the star's outer layer in interstellar space. If the star's mass before the explosion was more than 8 sun masses, a compact object is formed from the remaining matter of the star. This object is called a neutron star. If the star's mass was more than 40 sun masses, it is posited that a black hole appears after the explosion. As for the composition of these emissions, there's a large percentage of thermonuclear synthesis products, the remains of the process taking place throughout the star's entire life cycle. It is thanks to such supernovae that the universe in general and every galaxy in particular chemically evolve. It goes without saying that what I've told you about the nature of these events is largely theoretical assumptions. Man hasn't observed these processes from up close, and therefore cannot make definite statements about their nature. Nevertheless, thanks to the development of astrophysics, science is advancing impressively far ahead, revealing things unheard of in the past. And who knows, as time goes by, we will probably get closer to understanding much more complex matters. The list of puzzling celestial bodies in space around us may run endlessly. The reason for that is that science is still not able to give a definite answer to how fundamental things that the universe is made up of actually work. The discovery of yet another bizarre object is a rule rather than exception. And until we find the key to our understanding of the nature of all anomalies lurking in space, the solutions of mysteries in the universe will continue to elude us. And the thing that will remain for us to do will be to keep getting back to them, trying to give them some description.